Study under Vista Foundation wants public to appreciate mathematics, physics, all kinds of basic sciences. And today's evening we have Professor Arvinda from Tata Institute of Fundamental Physics and Practical Mathematics. So he's going to take us through a trek on tiling various kinds of domains. Just enjoy.
Thank you very much. Yeah, thank you very much. It's a great pleasure and honor to be among people younger to me, even 1 year younger to me. And and I can speak in English, and in between maybe I can speak in Kannada if some people want, no problem. And so this is, before that I would like to compliment the efforts of Vista Foundation to try and reach scientific knowledge to larger people. So it's my humble gift I would like to give. This is the book Ramanujan, Kannada translation of Ramanujan biography.
Yes.
For your library.
Thank you.
Okay, so I hope we are all ready for a trail. So this is on, basically the underlying theme is tiling, and I thought, and also normal perception about mathematics. Whenever we talk about mathematics, people think of numbers, but there are also shapes, and I thought, of course, shapes and numbers also go together, so that you will see. So we can begin, yeah. Sure. First slide, yeah. So, since tiling usually means, tiling the floor, so you want to tile the floor, a flat floor. So when you want to tile the flat floor, naturally, you would like to make sure of a couple of things. One is that tiles should not overlap, and they should not leave any gaps. Both of them are, of course, undesirable. That's how we would like to tile the flat floor. So normal tiling that you see, for instance, here is all square tiles, because you produce a certain number in the factory and you have to tile the floor, flat plane. So naturally you have to make sure that when you tile, it should not overlap, nor should it leave any gap, So how does one start with doing that with one particular kind of shape? Okay, normally people work with regular polygons. Next slide. So if you look at regular polygons, namely, maybe next slide, So regular polygons. We have seen that what is the constraint when you want to tile like that. So each tile would mean it has some corners, it has some edges. So when the corners around a particular corner, when you have tiled, which means the space around the corner is also filled up. So when it is filled up, so what should the angle around that corner be? I would like it to be interactive. So you can also share, 2 pi, right? 2 pi or 360 degrees, right? So that's all, the simple criterion. And when you look for regular polygons with tile, you have 3 possibilities: equilateral triangles, squares, and regular hexagons. The thing is that, as you know, equilateral triangle, the interior angle is 60 degrees. So if you put 6 of them, you get 360. And square and hexagon. And since from square I moved to hexagon, because regular pentagon, the interior angle is 108. And at each corner you have to put at least 3 of them. But if you put 3, you already sort of little less than 360, it will leave a gap. If you put 1 more, it will be overshooting 360. You can't do that. That's why you don't use only one. You can't actually tile the floor by a regular pentagon. And for the same kind of reason, you cannot tile the floor by regular heptagon and beyond. 7-sided regular polygons, because interior angle of a regular 7-sided polygon will be bigger than the interior of the hexagon, which is 120. So if you put 3 of them, it will overshoot 360. So these are the only 3 regular things possible. So that's a little too boring. I think people would say, only 3 tiles, what is it? There should be plenty. So you look for combinations of regular polygons. You could use triangles, squares, and so on. So then you get a lot more possibilities. So they are called Archimedean tessellations. I think Kepler classified many of these things, and Kepler is one, he called it Archimedean tessellations. And actually we see some of these tessellation being used. You would see this, and I think you may have seen this in some grills, and you would see the last one is quite popular. That's octagon plus square. 4, 8, 8. All these numbers means what the meaning is that at each corner point it tells you, for instance, let's just look at this one. At each corner point you have a 12 gun. At this point you have a 12 gun, then a triangle, another 12 gun. So that's what it means. So 3, 12 squared, or you could think of it this way: triangle, 12 gun, 12 gun. Yeah, that's all. 12 squared means 12 times, 2 times. Or here, when you see here, at each point it's 4 square and then a hexagon and then a 12 gun. So when you can do this. So I have said that when you want to look for combinations of regular polygons, just as you worked out with only one polygon, just 3 possibilities. The criterion is very simple. Around a corner point, the sum of the angles have to be 2 pi. So you get some 21 possibilities. But not all 21 possibilities can be realized. This is one thing in mathematics. Possible existence doesn't really mean uniqueness in some sense. Yeah. So you could have, and also you should be able to realize that. Yes. So only 8 more, apart from 3, totally 11 can be. You could see that you can realize only those of them. You do it only by. That's how they did it. You just have to do it by brute force. You take all these things and try and so on. Whatever fits, you see. If it doesn't fit, then you try to find out a reason. Yeah. Next slide.
So what does it mean? It's not possible to realize.
Yeah. I'll come to the next. It'll come. Yeah. Yeah. Go ahead. Next. So first, let me quickly sketch how I say you can cut down the possibility to 21. Yeah. What does it really mean? Interior angle of a regular k-sided polygon. It's a simple formula. It's pi minus 2 pi by k, and if you just simplify it, it is 1 minus half minus 1 over k times 2 pi. Since 2 pi is one full turn, I'll just kind of think of it as a full turn, and I have n number of polygons, which means different types of polygons, and each polygon, let's say, has one polygon has k1 number of sides, like let's say triangle, k1 could be 3, k2 could be 4, k3 could be 5, and so on. K1 to Kn, n number of polygons you want to put together, and if you want to put together like that, then the sum of the interior angles, right? This is the K1 sided polygon, regular polygon, will have the interior angle to be equal to 1 over 2 minus 1 over K1 times 2 pi. So I'll just take it of a full turn. Yeah. So if you add those things, you have to get 2 pi. 1 means basically I have used a full turn, times 2 pi is equal to 2 pi, so I have just cancelled off 2 pi, that's all. Yeah. So it has to be equal to 1. This is a very simple arithmetic. Okay, and if I simplify it, you will get this kind of a relation. 1 over k1 plus 1 over k2 up to 1 over k1, 1 over kn is n by 2 minus 1. This is what you will get. Okay, so you can solve, you can see how, first of all, you would actually easily notice that n cannot be really more than 6. The reason is, when you say a polygon, it has to have at least 3 sides, right? K1 is at least 3. Okay, and if I use a regular polygon, which means if I take a triangle, interior angle is 60. Okay, that's the smallest sided polygon I can put. If I put 6 of them, already it's 360. So if you take any other polygon, the interior angle is going to be bigger than 60, so it has to be less than 6 only. Yeah. So n is already 6, you will get that. That's how you kind of, it's simple logic you apply. So it already cut down the possibilities when you, this constraint, it will cut down the possibilities to some 21 only. And question, I mentioned that not all possibilities can be realized. Okay, so you asked the question. So I am giving you one example of a possibility. Namely, if I take 2 pentagons and 1 decagon, so pentagon interior angle will be 108. So if I put 2 of them, it will be 216. It is 144 less than 360. And decagon, 10-sided polygon, interior angle will be 144. So they add up. So if I put 2 pentagons and a decagon at that vertex, you actually can match 360. Okay, so it's possible. Okay, so next slide. So you have to try to put it. If it really it's a possibility, but you want to really tile the floor, right? So you want to have a certain number of pentagons, certain number of decagons, and want to tile the floor. When you want to tile the floor, you should not leave any gaps and so on. Yeah. So Kepler tried to put these together. Yeah. So no, previously, yeah. So he tried. So as you would see here, you have a decagon and you have two pentagons. You put it here. This is fine. After you put it here, you try to do tiling, but then there is a gap here. There is a square here. I mean, this one here, and sometimes these two decagons also will overlap, and so on. Yeah. So he tried several patterns. Actually, in his book called Harmonis Mundis, I think, I mean harmonic world, I think is what it means in Spanish or whatever, Latin. So that he tried several patterns. He couldn't tile. Okay, so well, you couldn't do it. Yeah, actually, you can actually show arithmetically or whatever with a nice logic that if you have a regular pentagon, among your collection of regular polygons, you cannot really tile the Euclidean plane at all.
Yeah.
Yeah, you can prove it. Yeah, it's actually, when some of the things that I tell you, you can think about it, and so yeah, it's nice to think about it. And now that you could put your Google search to a better use and see why it's not possible. After you have thought quite a bit, then you find an answer. Then you will appreciate it. Yeah. So I would rather like you to do that. Yeah. So this is the problem. But this is a nice picture. That's why I wanted to show. And another thing I want to say is that in research, research meaning when you want to become a mathematician or something. So what happens is that you will always be stuck with problems. It's very, very rare that you find solutions. When you find solutions, you're happy. Okay? Not only just happy, you're ecstatic. So a failure doesn't really mean it's a failure. Because failure may not be, it may not give you it may not be sort of what it means that you may not be able to understand why it is failing. Okay, so you keep that. The thing with research, honest, intense, sincere research is that a failure also stays in your mind just as success stays. So over time as you work, sometimes something else happens, then you say okay, because it has stayed in your mind, you can connect up two things. And it could be the same person or it could be a generation of people. Okay, so in this case I am just talking about a generation of people. Kepler tried this, fine. It's a nice picture, people can appreciate. You can make a nice window of this shape or whatever, grill or something like that. I think it's nice, yeah. In fact, some of the Muslim architectures, by the way, have this kind of thing, yeah. I did see that. I mean, not exactly this one. If I saw exactly this one, I would have taken a picture. I saw hexagons and so on in Kashmir recently. But I mean, you have this kind of nice things here. So I'll come back to this, by the way. The reason why I said failure is because, but this pattern was beautiful. It motivated or inspired someone to come up with a very beautiful kind of tiling. I'll come back to it later. I don't want to sort of, I want to keep the suspense, yes. Yeah, next. Okay. So now, the next problem is, regular polygons we have understood. Using regular polygons, Not everyone wants, somebody, regular polygon for some people that may be good. For some people, why regular polygon? People can ask a lot of questions for sure. Okay. So I like a particular triangle, let's say an isosceles triangle, let's say I like it, I want to tile. So if you ask the question, if I can use any triangle, can I tile? Yeah, it's possible. The answer is very simple. You can think about it. I'll immediately kind of give you the answer. Any triangle, by the way. Any triangle. The side lengths could be different. The angles could be different. If I have hundreds of those triangles that I like, I can tile the floor without leaving any gaps and overlapping. The solution is very simple. What you do is you take any two of those triangles, and say one of the sides I take, that side is repeated on the other one, so I just invert it like that and put it. So what I get is a parallelogram. You can get a parallelogram. And once you have a parallelogram, you know how to tile it. Right? Rhombuses and so on, you can tile. You just put the parallelograms together, and I'll show you a picture later how to use parallelograms to tile. So any triangle, you can create a parallelogram and you can tile. Okay. So triangle we have understood. So let's go to 4, quadrilateral. So quadrilateral we have seen squares and rectangles also we see, right? We see the tilings with rectangles. So how about irregular quadrilaterals? Side lengths and so on different. So let's just confine ourselves to convex quadrilaterals. See, when I say convex polygons, what I mean by convex is that given any 2 points, when I draw in a straight line, it should fall within the tile actually, that kind of thing. Yeah, that's just a simple constraint. It's not such a serious constraint. So I take any quadrilateral of any shape. I have made hundreds of them. I want to tile the floor. I can do that. Yeah, I have just given one particular example. You could do it. What works out, I will tell you why. So any convex quadrilateral you take, the sum of the interior angles is 360, and that is what comes to use here. So at a corner, since you want to make 360, you arrange 4 of your quadrilaterals in such a way that at a corner all the 4 angles meet. So here, for instance, I have named A, B, C, D here. For instance, here all the 4 angles come here. Since I know that 360, I come here. So which means this particular pattern, let's say, this particular pattern, 4 of these put together, you can tile. Yeah? Okay? Next slide. So any quadrilateral you can do that. Yeah. So I just thought I'll just show you inspired art. Yeah. This Dutch artist called Escher, MC Escher. I'm sure all of you have heard of his great works. So he used tessellation to create nice art. Okay. So for instance, this is what I meant by a parallelogram. Yeah. Any parallelogram you can tile. So he just used that and see. Okay. I mean, somehow he imagined combination of parallelograms. He could just try to put this bird and the fish pattern, and somehow he brings it here. He very carefully worked. It's a nice art. Yeah. Next one. Okay. So from 4 we have understood, right? Any convex quadrilateral, irregular quadrilateral, I can tessellate, tile the plane. Tessellation and tiling are the same. Yeah. So now I should have actually gone to 5, but I have gone to 6. Yeah. Okay. 5 somehow seems to be creating some problem. We will see what it is. Yeah. So let's come to 6. So we have already seen regular hexagons, but again, if I want to work with irregular hexagons, okay, unlike squares and triangles, I cannot work with any irregular hexagon for tiling. For tessellation, because the angle sum now is 12 into 6, so 720. So okay, so it's, you have to sort of, to meet the criterion of around a point 360, you require you have to, I mean, the hexagons will have to satisfy certain criterion. Okay, as far as back as 1918, about 100 years ago, a student of David Hilbert, his name is K. Reinhardt, he actually, it's a simple arithmetic perhaps. I haven't seen a proof of it, by the way. I'm trying to see a proof of it, but I think it should be simpler. Some of you can actually try and see it. He classified what kind of hexagons can tile. The types have to be either, like something like he has given this particular thing here, certain angles, some angle and side criterions. If they meet those criterions, only you can tile. For instance, the regular hexagon satisfies all the 3 criterions. Okay. But if hexagon satisfies one of the 3 criterions types, it has to tile. Not only that, any hexagon which tiles, irregular hexagon which tiles, has to fall into one of these 3 types. So he completely classified that. Only 3 types of hexagons can tile the plane. So if so you have to be careful now when you give your mason or somebody to make tiles, when you give this specification, make sure that it has to be, if the guy makes some mistakes, then you cannot tessellate. All your 100 tiles will go waste. Okay, so this one has to be careful. Okay, but the criterions, only these 3 criterion. This is a theorem. So now he also looked at pentagons. I call it the puzzling pentagons. So Reinhardt himself classified found 5 different types. Like just as a hexagon, 3 different types I mentioned, angle and side criterion. He found 5 more types of pentagons which can tile the plane. I mean, he wasn't very sure whether it's all the 5 or more or something like that. He didn't state anything, but he found 5 of them. Perhaps the problem wasn't very interesting. So 50 years later, somebody else looked at it, and Kirchner, he looked at 3. He got 3 more types, 3 types different from. But Reinhardt had mentioned that it would be interesting to see if one can classify what types of pentagons, just as to see if, how he could solve the hexagon problem. And by the way, he didn't mention it, but it's also easy to see irregular polygon with more than 6 sides, heptagons, whether regular or irregular, you cannot tessellate the plane. That's also not a hard this thing. That's again a nice this thing for you. When I say not hard, it doesn't mean easy either. It's elementary but not simple. Okay, but you can do it. It's a nice way to kind of look at it. It's one way for you to kind of take the problem, look through things, and then go over and try to understand. You may yourself come across a nice startling result. It will be really nice. Go on a journey like that, and this doesn't really require much sophisticated background. Okay. Anyway, so he found 3 more types. 5 plus 3 was now 8. Yeah. Next slide, please. So these are the 8 I mentioned. And in 1975, what happened was, around that time somebody said, okay, I can show that only 8 types are possible. It's not Kirshner's. He proved it. He said, I have a proof of it. But soon one realized that the proof was faulty. And proof, it was, I think, I don't know if it was Richard James who found the 9th type, who found it faulty, or somebody else. Somebody else found this thing. Richard James can actually made it very clear that the proof must be wrong, because he found a 9th type, a kind of counterexample in some sense, 9th type, which could tile the plane. Okay. So because of that, Martin Gardner, a delightful column writer, he is basically not a mathematician. He is a mathematics teacher. Not a practicing mathematician, but he is really the master of communicating to larger public, and I think we need such communication here in our country. And I would think Vista Foundation, I wish all it well if you can take it forward. Yeah. So in Scientific American, you must have heard of this magazine. Lovely articles actually. I remember in my PUC also in National College, I was inspired by many of these articles. Very beautiful articles. Yeah. The thing about that time is that the student time is the enjoyable time. Something excites you. You really may not understand everything, but you know that there is something very happy, very pleasant about it. Yeah. And that's nice. So articles need not have to say, everyone has to understand the theorem, proof, or something like that. If it excites your interest, inspires you, that itself is very good actually. Okay, coming back to this. So when he wrote in 1975, it suddenly, look at his this communication. So a lot of people started looking at pentagons. And this lady called Marjorie Rice, she is now a history name in some sense, in the sense that she's just a homemaker. She just had high school mathematics background. So she liked reading that article, like an article in Sudhar, Tushar, one of these magazines, famous magazines. So she saw the article, and she herself, this homemaker, so she found out 4 more types. So 9th was found, 4 more types. 9 plus 4 is 13. And then a graduate student, like one of you, MSc student, German student, mathematics student, Rolstein, discovered a 14th type in 1985. Okay. So there are these types I have mentioned here, yeah. So this is how it tiles. And even then one doesn't know whether 14 types is all, are there more? Okay, still this one. So next slide. Oh, I call it breaking news because I lectured last time in May in some places. I said 14th and this is all that is known and so on. A month later, couple of months later, of course, breaking news in TV would mean, it has to happen today or something, but I think in mathematics, as I said, success in research is very rare to come by. So last year's result is still a breaking news. So last year's result, so in July 29th, these people, by exhaustive computer search, of course, not just computer search, you have to you have to use some logic and so on, they discovered a 15th type of pentagon, irregular pentagon, which can tessellate. And here you'd see all the angles, all the sides different, and you can even take the side to be 1 over some 2 root 2 times root 3 minus 1, some irrational kind of thing. Yeah. So now the problem becomes interesting in the sense that, why are we thinking of classifying? Maybe there are infinite, I do not know. Nobody knows. Yeah. It's an open problem. It's a nice open problem for any of you to really look at it. Okay. Usually number theory you can state problems very easy to state, but the solutions comes after 2-3 many years. There are many problems the solutions haven't come. This is a nice geometry problem. you could say 100-year-old problem because Reinhardt started it, and so this was just as last year. So if you find a 16 type, you will make another breaking news. I'm sure you are capable of doing it. Next one. So the current status is these are the 15 tiles, 15 types, and next slide please. So I given the specification here. There are these specifications. By the way, I found all these things over internet. I mean, of course, in the internet you have to be a little careful also. Sometimes not all Wikipedia thing is right. So you don't take exactly what is there. you use some of your logic before you go public, yeah. Because not all news that you get in the Google and internet and various things may be right. You have to really see which are really authentic sources, right? I mean, because otherwise, these days you might really kind of see something and then you don't want to be ridiculed, that it was a silly mistake kind of thing, yeah. So be careful. But still, I mean, I got it out of this, yeah. So these 15 specifications. Yeah, next please. Yeah, just a second. Sorry, let's just go back a little bit. I just thought sometimes, okay. So here, let's say the reason why I wanted to show the next the one after that was, see this one somehow looks very similar, right? I have this here, just looks like a blown up picture, and that one also looks like a blown up picture. They look very similar or the same because of this line here and so on, but the side lengths are different, and that really gives you different specification. Next slide please. So I just wanted to say, so these three, they look very similar kind of thing, but they are different specifications. So that's why I said problem, a little careful, you have to be careful. So it's an open problem. That's why I called it the puzzling pentagons. And if Majori Rice, a homemaker, could make it, I'm sure anyone can make it. Shruti can make it, I think. Honestly, yeah. I mean, when I say like a joke and hard problem, it's not really a joke. I mean, this lady did it. So we have to believe in ourselves. Well, I can do it perhaps. If the problem really has gotten into your head, you might want to do it, yeah. It's useful. So next, let me come to this. So tiling, I think more or less I have kind of covered that topic. Since I'm footloose, I want to just kind of on the tiling. I want to go on a slightly different journey altogether. So what if some of the angle is less than 2 pi? I cannot tessellate. I cannot tile the plane. But I gave the specification. The mason made this. So what do I do with this? I end up with this. So I make boxes out of it. Yeah. Okay. So it's less than this thing to 2 pi means there's a gap. So you bend things so that sort of fill the gap. Yeah. In the sense that when you use I use regular polygons to tile the plane. Now what I use regular polygons to make boxes, let's say, or polyhedrons or regular solids as they call them. So when I want to make regular solids, again it's very clear that hexagon and beyond I cannot make, because when I want to make a regular solid box, at least at each corner point at least there should be 3 faces. But if I put hexagon, already 3 faces, if I put it's 360, there is no room to bend. Heptagon is beyond is anyway out of question. So up to pentagon I can do, right? So at least 3 faces have to be there, but there could be more than 3 faces also. So if I use equilateral triangle, I make one at this vertex, 3 faces meeting. So this is called a tetrahedron. This one is the 4 faces meeting, tetrahedron. By the way, without defining anything, I am telling all these things, yeah. Which means when I say defining, what I mean says that in the tessellation or a box when you make, you would want the specification of the vertex to be the same, in the sense that number of edges meeting have to be the same, number of faces have to be the same, meeting have to be the same. That's the criterion met everywhere here, like the tiling also, yeah. So 4 you can make. This is called the octahedron, and then I have the icosahedron, 5 of them meeting. So now what vertex, can I make a box with more than 5 equilateral triangles? Can I make it out of 6? Yes or no? No, why?
In the 6 equilateral triangle, the corner has
60. So there is no room to bend. Excellent. So beyond 6 also is not possible. So this is one case where 3 are possible and they can actually be realized. That's what I meant. You remember my earlier statement. The 21 possibilities, only 11 of them could be realized. Here, there are 5 possibilities, namely with triangle 3, with square 4. I cannot, it's a square, that's the 4th possibility. I cannot make a box using 4 squares at a corner, because if I put 4 squares at a corner, I'll already be 360. At least 3 faces, so 3 faces, and again pentagon for the same reason. So there are 5 possibilities, and all the 5 possibilities can be realized. And these were known to Greeks, and so like they also had significance. For instance, tetrahedron was fire. Like Panchabhutas, they also had the earth and signifying these things. So there is a lot of similarity, and so if you use, so again you can make boxes using these 5 boxes. Now, like tessellation, let me use combinations. I'll use combinations of polygons to make boxes. Okay, again there have to be finitely many only, because when I use the combination also, now the criteria is less than 2 pi or less than 360. So that gives you already finitely many possibilities, regular polygons. And they are called Archimedean solids. That's the next slide. And you get 13 of them. So 5, 12. Yeah. These more. And the thing is that, I'll come back to it again. Why is this interesting? Yeah, both tessellation and, please. Both tessellation and boxes, I'll come back to it again, later. So for instance, this is what you would have seen as a football, and this is also called the buckyball, and I think a carbon 60, I think sometime in the 1980s, they discovered one type of carbon with carbon 60, this kind of molecular structure. Yeah? Fullerene, Buckminster fullerene. It's called buckyball. And apparently some of the viruses have some of these shapes. Indeed. So these are the only possibilities. I mean, as I said, possibilities could be many, but those which can be realized are these. Okay, so I thought I'll just add a little bit of logic or whatever, little bit of mathematics. Not that I'm not talking about mathematics all this time, but tiling. I talked about what's called Euler number, I thought. See, all the shapes that we meant boxes, they are all hollow inside. In other words, they are called convex boxes. Given any two on the boundary and join the straight line, the line inside the box. That kind of boxes I have. They are all different, different prescriptions and so on. But there is something which is, in mathematics, as I said, geometry, you study shapes. So all of them have something common. What is common? Like the football, if I have made balls out of all these different 13 plus 5, 18 of those boxes or whatever balls, like a football I made out of leather patches, let's say, and blow air into it, all of them will become balls, footballs, spheres, right? There's the same shape. They don't become like a inflated cycle tube. That's a different shape, right? Inflated cycle tube is a different shape. So, how do I kind of see all this? So, there is a nice shape invariant in the sense that the reason why you get that same shape is also, it's sort of, there is a underlying structure behind it, So, as we saw, now when we look at the boxes, so what were they made of? They were made of regular polygons. A regular polygon, what is it made of, composed of? It has vertices, it has sides, and it has a face, right? So vertices is like points, sides are the edges length. So if you think of points as 0 dimensional, side lengths 1, and then the face 2 dimensional, and I made boxes out of it. Okay, so when I make boxes, the boxes will have a certain number of corners, vertices, certain number of edges, certain number of faces. Okay, so that's what I call for each polyhedron box. Now I'll say, okay, I'll now get myself completely, instead of working with regular ones, I'll make boxes out of different ones. Sometimes, when you want to really do this, sometimes there is some, you do it all very regular, very nicely, but sometimes, when you want to put the box together, you may have made some miscalculation, something like that. Another polygon that you want to put may not be regular. You make a box out of it, but still the number of vertices and so on is the same. So for that, you look at this expression. number of vertices minus the number of edges plus the number of faces. Okay? You might wonder why should one look at that expression. There is some logic, but let's not get into the logic always. It's always nice to sometimes leave it for imagination. I prefer to leave it for imagination. Yeah? You can try to understand underlying logic too. There must be definitely some pattern, some reason why Euler looked at it. Okay. So is there anyone in the audience who is not familiar with this? You can raise your hand. Or is there anyone who is familiar with this? All of you are familiar with this?
Yes.
So I can go over this quickly, I think. Yeah, that's what I wanted to know. If anyone is seeing for the first time, I wanted to count, but all of you are familiar. Excellent, very good. So you know what is the number then? Yeah, I would like some. You have had some tea, I think, right? Yeah, 2, right? Yeah. So that's a constant. That's a shape invariant. Okay. So inflated cycle tube will have a different Euler number. What is the Euler number for that? Huh? Somebody said 2? No, it's not 2. If it is 2, it should be the same as this one, yeah? For the inflated cycle tube, suppose you made out of triangles.
I think they are not computed for the.
Exactly. So now, see, now beautiful thing. You compute it for you know it, but I mean, have you actually done it? Have you counted it? Don't take anything if one says it. I mean, if I say it, just don't take it like that. You have to see it yourself. Okay? That's the only way you internalize a concept. Otherwise, there's no use really, honestly. Okay? So you have to count. And count what it is. Actually, you can first make a guess and see how to count and so on. Since he says you are familiar with this, you should be able to kind of do that. If not, you'll bug him. And but more than but before they bug you, make sure that they actually make one box and count.
Exactly.
If they do not count, just if they have not made it, just don't entertain. Okay? We don't want all theoretical answers. We want it to be done. It should be right there in front of you. And this shape actually can teach you. And that's the only way to learn, by the way. There's no route to shortcut to success, as they say. This is what I mean. You have to do it. Okay? Since Euler found that the expression is the same for this one, and for any object which kind of, when you blow air into it, it makes into a cycle tube, let's say, that shape will also have the same number, and that will be 0, by the way. I'll give you. Next slide, please. So that's called a shape invariant. So you can get the shape invariant like that. So I just gave you some things. This is a cycle tube made out of triangles. Usually you put mathematically called the genus 1, genus 2 and so on. And it's very easy to count. If it has one hole, it is 0. If it has 2 holes, it's minus 2. If it has 3 holes, it's minus 4 and so on. So this is what I have given you. I would like you to make at least one box and count and make sure it's right. And also try to find a logic. Do you have, by the way, then you know it. Do you know a proof of that fact that a box, for a given box, V minus E plus F is 2? Do you know a proof of that? Yes or no?
They are not seen.
They have not seen a proof. It's very easy. Yeah? It's very easy actually. I'll give you, since I'll tell you how. So, suppose I have a box. Let's take a square box itself. That's good enough. Or a tetrahedron.
It's a matchbox.
Matchbox. And you know you have the number of corners, edges and the faces. And you know the expression is 2. I would like you to be loud. You are very this thing. Yeah. I want you to speak. For me, I mean, it's like I would be speaking to a wall. I don't want it that way. I want interaction, please. Yeah? Not that. I demand interaction. Am I being too abstract? No? Yeah. Okay. Please participate, because I will get the energy from you. It's like you charge my battery. Otherwise, my battery will lose charge before the talk ends. And I don't want that to happen. I would like to be, faithful to the Vista Foundation, or I really like their efforts to. Okay. So please participate. Okay. So if I remove one face, which means, like say I had the box and I just removed the lid. I have opened it, right? Okay, so what should the count be? Number of vertices minus number of edges plus number of faces. I have removed one face. What will the count be? Earlier it was 2, I removed 1. So what should it be? 1, yeah. Okay, that's all right, 1. And I keep removing them, yeah. So what happens is that each time you remove, beauty is that when you remove one face, let's say, you make sure how many edges you have removed and so on, yeah. So when I remove, let's say I have the square box, I removed 1 and you said it's 1. I remove one more, let's say. When I remove one more, I have removed one face and I have removed one edge. But the number of vertices is still the same. Okay? So now you calculate the expression V minus E plus F for the removed, for the, after you remove that. It will still be the same. Because I have removed one face and one edge. So one face and one edge cancel out each other and V minus E plus F is 1. So I remove, each time you remove, the number seems to be constant, will be constant. That's how you prove it. And finally you are left with, if I keep removing them, you are left with only 1. When I left with only 1, let's say in the square, I am left with only 1. So in the square, what is the number of vertices? 4. Number of edges? 4. Number of faces? 1. So what is V minus E plus F? 1. So you left with 1. That's what you wanted to prove. Each time you add something, edge becomes common. V minus E plus F is 1. V minus E plus F is 1. You do it, and then you have a opening and you close it with one face and it becomes 2. That's actually a proof, by the way. Okay? So now, do you feel better? See, the fact that you did not know a proof is because not that you are not capable. You never try to think about it. Okay? If you want to be mathematicians or if you want to do any this thing, if you want to be teachers, anything, you have to think yourself. Unless you think yourself, internalize, you are not going to be a good teacher, you are not going to be a good researcher. This is a very strong message, by the way. I mean it. Every success, every this thing has to undergo a process of hard work. Okay? And hard work doesn't really, if you are not enjoying it, don't do it. Please don't do it. You do the hard work only if you enjoy it. Okay? It's a message actually. Since you are all young, I really mean, every word of what I say. Okay? Because all researchers, everyone goes through really, sometimes the problems take ever to solve. You can ask any professional mathematician, they will always be having some problem which they have thought for 5 years, 10 years. And even I can say from my experience, in 1990 I am thinking about a problem, still I am kind of wondering. Okay? So it's like 25 years I'm still thinking about some problem. It's there, but I mean, you make certain progresses. It's very important. Okay? So you have to put hard work, and you put hard work only if you enjoy. If you are not enjoying it, that may not be your cup of tea. Please do something else. Do something only when you enjoy. Otherwise, just don't do it, honestly. Because as I said, you are always stuck with problems. It's a frustrating period. Only if you can endure it, take it. Otherwise, don't. Yeah. Okay? It's good for you as well as for it's basically good for you. Well, subject anyway will live on its own. It's good for you. Okay? Subject doesn't depend on you. You depend on the subject. Yeah. Your life depends on the subject. Yeah. Sorry, am I overshooting my this thing? No. Yeah. Thank you. Because I just take a simple example. So you see, when I explain the proof, you could understand, right? You think, when you see a nice result or something, see if you can prove it. Okay? One way to prove, let's say if you see a nice theorem, there are two important messages I would like to convey. One is, you have to solve problems. In any textbook you take exercises, keep solving them. You don't try to read the material first and then solve. You start solving the problem, then you know that, well, I need some material, then you look at it, so that you will know how to use the tool. It's almost like you have to tighten some screw or something like that, then only you look for a screwdriver, right? It's exactly like that. You have all the tools, but you don't have anything to practice. That's also not very good, honestly. Yeah. Please, it's very important. Yeah. So solving exercises is very important. When you want to understand a theorem, try to see an example where the hypothesis of the theorem is satisfied, and look at the example and see if the conclusion of the theorem is satisfied with the example. That's one way. That's typically the way people do in research. That's how you understand One referees papers exactly like that. Okay, the statement says something. Instead of starting trying to proof, I mean, because I'm a professional mathematician, I need to referee papers. What happens is that when you referee a paper, it's not like a textbook. You see, okay, this statement is there, you write this way. When you see a statement of a theorem, well, you see whether, I mean, naturally you start refereeing because you know something about it. And then you see, okay, well, how to do this. So instead of looking at the proof, then you first of all see if there is an example, let's say, which satisfies the hypothesis of the theorem. Examples are very, very important. And then in the example, see if there is a conclusion drawn, you can draw it for that. And quite often, if you can actually conclude, the proof will be quite like that, honestly. Quite often, more often than not. Of course, I mean, I'm saying a very simple fact, but I mean, that's the guiding principle. If you can solve in the example, then you have a way. You see what kind of things that you use in the example and see a proof. And then that's how you find mistakes and so on. It's not that one looks for mistakes. You see that flaws that way, yeah? It's a hard process. Research and creativity is hard process, but it's enjoyable. Okay, so after that message, what I'm trying to say is that please do it. Statements, yeah. Next one. Yeah, I still have 15 minutes. Okay, so now I am footloose, so I am going on another detour. I am taking on another journey. Boxes and Euler number, shapes you understood, shape invariant. Now I will take on a non-Euclidean detour. What do I mean by non-Euclidean detour? So when I had these polygons tiling the floor, the corner this thing had to meet, it was 2 pi, 360, and boxes it had to be less than 360. Suppose you have more than 360. Okay, you cannot tile the Euclidean floor. Okay. But what I am trying to say is that there is a lovely concept of what is called a non-Euclidean geometry, which took 2000 years, by the way, to kind of come to an understanding. So I'll not really, dwell too much upon that, because I mean examples. So non-Euclidean geometry would mean that it's something which is not Euclidean. One of the things that you see in Euclidean geometry is that you studied in high school is that, which I already used. If you take a triangle, sum of the interior angles of a triangle is equal to what? 180. Correct? 180. Okay? But then, if you take the surface of a sphere, surface of the earth, let's say, or even a watermelon, let's say. When you see a watermelon, you would see it's not a flat one, right? It's a spherical shape. Actually, by the way, you do find really round watermelons or melons. You have these kind of curves that you see. When you want to cut two, I think all of us know, if two people have to share, they want a really good share, so they exactly cut it. How do they cut it? You take at one point, and when you cut it, the knife has to pass through the center. It's called, and then it gives you an arc on this thing. That's called the great circle. And so those great circles are straight lines on that ball, yeah? Just because everything is not flat, we know that, right? Even you don't have flat watermelons. In Japan, of course, they are trying to do cubical this thing and so on, but that's a different matter. The nature, what does nature give you? It gives you a spherical one. So there, I take from the North Pole, okay, and then I move along one of those curves called the great circle. I come up to equator. When I come up to equator by the equatorial circle is also a great circle. When I hit the equator, the angle is 90. Okay? And from North Pole, I start at an angle at 90 degrees to this and then move here. Again, I will hit the equator. Again, I will hit the equator at 90. So I got a triangle, one part of the equator, then these two things, both are great circles. I got a triangle with 90, 90, 90. So it's already overshooting 180. So you have, what I mean is you have shapes where the natural triangle is called a geodesic triangle, because these great circles have a very nice property of minimizing the distance, locally minimizing the distance. These geodesic triangles, there are shapes in which the straight lines, when you take a triangle like that, the sum of the interior angle is bigger than 180. And there are geometry and shapes where you have triangles, the interior angles is less than 180. So if it is less than 180, you can put several of them and tile, right? And that's what the non-Euclidean plane it does here. Okay? So this is in some sense, this is the Pentagon. For the Euclidean eye, these two looks very different, but for the non-Euclidean eye, these two are the same. They are isometric. Okay? So you have to work with the non-Euclidean eye. And for instance, not only Pentagon, you can tile the non-Euclidean plane not only by regular non-Euclidean pentagons, but you can also tile by non-Euclidean regular octagons. And you wouldn't believe, the possibility is infinite. If you give me a million-sided non-Euclidean polygon, I can still tessellate. Okay? So non-Euclidean geometry is really huge. And you will see, my point is to kind of say that these are all very natural, yeah. Okay? Okay? So non-Euclidean geometry gives you these possibilities, and this is one, this thing, yeah. Next slide, please. So I wanted to kind of, again, I showed Escher's inspired art. Now I will show Escher's inspired art again. Here he is inspired by the non-Euclidean tessellation, tiling. So this you see very similar to the previous picture that I showed. These curves, by the way, the curves that I showed in the previous picture, these ones here, they're all straight lines in this geometry. They are geodesics in this geometry. So you find these kind of things. For instance, you have a hexagon here, right? Yeah, and so there's this picture, and just as previously he used parallelogram kind of thing to get the fish and the bird tessellation, he is getting the devils and the angels here, I think, or maybe I don't know what it is. Not the devils and the angels, but something else, I think. Yeah, it's like a fish, I think. It's yeah. So the reason why I showed this, because he uses this tessellation and get this. So this is a picture of non-Euclidean geometry. So as you would see, as you go farther and farther, they look small. They look small for the Euclidean eye, but actually they are the same. This fish is the same as this fish. They are isometric. Yeah? In the non-Euclidean geometry. Okay? You think it's something very abstract, no? Right? Yeah, fascinating, yeah? So equal to 180, bigger than 180, and less than 180 also you have geometries. And this is one example. Next slide, please. And there is another model for the non-Euclidean geometry. It is called the upper half plane model. Even the upper half plane model also, this fish looks very big and this looks small, but they are exactly the same. And he created this picture first by working out this picture. So where, look at this, so there is 1 here, then it becomes 2, okay, and then it becomes 4 here, and then 8 and so on. So it's increasing in 2 power, whatever, powers of 2. And he gets a pattern here, and kind of here he keeps repeating them. So it's very easy. You look, it's a very difficult art, you think. All he is using is tessellation. Okay, just a style you repeated like that. In the non-Euclidean tile also, you make a picture, but only thing is you have to proportionately reduce the size and so on. That's exactly how he did it. So this is a picture from his book, by the way. I mean, his book. It's not, I'm not doing any this thing. All Escher's book.
Is he read non-Euclidean?
Oh yeah, I suppose so. Must be. He must have. He brought many of the scientific things into that. Yeah, he's an artist basically. Okay, so just hold on. Yeah, no, that's fine. Yeah, next slide. Yeah. So here again I show another geodesic pattern, right? It's a non-Euclidean geometry, and these are all geodesics. This is not very different from the kind of thing earlier I showed. It's a nice geodesic pattern it looks like. Next please. I called it geometry in nature, right? I take 2 pictures from nature now. This is nature has created these. This is a lily and lotus leaf thing, and you would see these ones here. These are all the veins, right? Venation pattern veins. See, they go exponentially like that, right? 2 here and then 4, 8 like that. It's similar to the kind of thing that Escher used in his this thing to create non-Euclidean picture. And these Venetian patterns, non-Euclidean geometry. So you think it's abstract, it took 2000 years, it took 2000 years for man to understand. But in nature, you know, it's there. They have figured out by time-tested methods, yeah. That's Venetian patterns are basically modeled on this, yeah. And here again the same thing. Don't you see some similarity? I think you would see some similarity. I'm not proving a theorem here, but I'm just showing the similarity here. And It's not exactly Euclidean, non-Euclidean here, but I mean some very similar to that. But you can, it's the same thing. It's called conformal. It's a conformal metric. So it's the same thing. See, again, when you went here, there are several of these going there, and you will see several of these. And that is why, actually, in the non-Euclidean geometry, as you go towards the boundary, you make more and more space. Okay? That's the reason why the leaves actually, a big leaf, the reason why they curl is basically because it has to kind of make way for more and more of these exponentially increasing veins. Or a tree, let's take. Another way to kind of non-Euclidean geometry is, let's take a tree. What does it start with? It starts with one stem. Okay? One stem, let's say 5 feet or something like that. But by the time you go to, let's say 15 feet above or 20 feet, it's already a huge canopy. How is it achieved? Then there's this branches, then the branches, everything increases exponentially. Any exponential increase is actually a sign of negative curvature actually. That's the point I wanted to make sure here. Okay, there is some tree called Hoka I have seen where everything just breaks exactly, bifurcates like this, 2, 2, 2, 2. It's a power of 2. So it's like by the time it reaches the fourth branch or so, it's exponentially increased, and then you can it gives you a nice shade. So nature, you see, is quite a lot of non-Euclidean geometry. So now I move on to, because I am footloose, I want to move on to something else. I want to come back to my tiling. I am still on the tiling, non-Euclidean tiling. Now I come back to some other tiling, and I talked about tiling. And where do you see tiling? Here we created these tiles and flooring and so on. But where do you see tiling patterns? Patterns that we saw in the tiling. So in solid state physics, you know that matter is kind of made of, basically they classify it into two kind of things: crystalline solids and amorphous solids, or non-crystalline solids. Yeah. So crystalline solids are those which kind of, in the molecular structure, you have one basic unit and that kind of gets repeated. Yeah. Crystals, right? And to study crystals, there are several crystals. How do you study them? How do you classify them, understand them without breaking them? So what you do is you analyze them through an electron microscope. Basically, you flash a torch, and because it's crystal, which means it's made out of, again, polyhedrons put together, right? So there are these phases. The light gets reflected and so on, depending on the angle. So when it gets reflected, there are what are called interference patterns. I'll show some picture a little later. The interference patterns are there, and then they kind of interference, and you see certain what are called the Bragg peaks, where the intensity is very high, and those Bragg peaks kind of tell you what kind of pattern the basic structure of the crystal is made of. Next slide, please. So these are actual electron microscope pictures of certain two crystals. I didn't get the name, some zinc alloy or whatever, some alloys. When you shine torch or whatever, see through the electron microscope, what I meant was, depending on the phases meeting and the interference patterns, we get something called the Bragg peaks. It's already 5:30. I'll just take about 5 minutes more, not more than that. Yeah, less than 2 or 3 minutes more. Yeah. So there are these peaks that you see. The crystal itself has a nice structure. It has one basic unit. It has a certain symmetry, and you see the symmetry by looking at this diffraction pattern. This is called the Fraunhofer diffraction. So when you see it here, so you can already see here, don't you see a tessellation here? It's a square tessellation tiling, right? This square pattern, so you will see squares, right? So it's a fourfold symmetry, and that crystal, for instance, has, you would see an octagon here, and if I put 4 of them, I get octagons and square. You remember you saw something in the Archimedean tessellation. So the crystal structure, when you look at the diffraction pattern, by studying the pattern, diffraction pattern, basically the Bragg peak pattern, you can actually relate it to tessellation, and since you have classified tessellations, you can understand what symmetries it is. So it's this whole of crystallography is based on this kind of study, group theory. That's all. As simple as that. Yeah. Next slide. So I talked about something called quasicrystal. What is this quasicrystal? It's something. So this quasicrystal was an object which was discovered by this person called Daniel Shechtman. By the way, he was here in India just earlier this month at the Indian Science Congress, Mysore. Dan Shechtman gave a talk on quasicrystals. Yeah. So I happened to meet him. I was there at this thing. I couldn't attend his talk for some reasons, but I talked to him. Mentioned he actually spoke about these things. Yes. So he in 1982 he stumbled upon a kind of object, crystallized subject. This thing, it had a diffraction pattern like this. It did not look like the diffraction pattern of any of these our regular tilings. As you see here, for instance, when you see here, you see a pentagon here, right? When you close in here, you see a pentagon here, there is a small pentagon there, and then there is a pentagon here, and so on. So there is this pentagons, and we have seen that the pentagons, especially the regular ones, create a lot of problem, right? So, but you saw a crystal structure in nature which has some pentagons here. What's going on here? It's not really like any crystal. It's looking like a crystal. So as it's called quasicrystal. Yeah, that's why I called it quasicrystal. Later on people called it. Since it's so unnatural or whatever, since it was something which was not known to people ridiculed. Even a twice Nobel laureate, Linus Pauling, ridiculed him. So he thought he was just bringing something, yeah. But well, I mean, he was sure of what he did. By the way, this is what I meant by interference patterns. So the phases, light, this thing. So you would see this when this is the where the intensity is more, intensity is less. This is what contributes to Bragg peaks. Bragg is another Nobel laureate. Bragg, B-R-A-G-G. So his this thing. So he called it quasicrystal. Okay. So quasicrystals exist in nature. And of course, there is a beautiful study of all this. And what is the tessellation? What kind of tiling that is give rise to this quasicrystal? Because it's pentagon, it's not similar to the kind of tessellation that I had described before, right? Next, Penrose, a physicist, in 1971, he kind of he created this kind of tiling, tessellation, which goes radially actually in some sense. It's called Penrose tiling. The building blocks were these two things, the blue diamond and the green diamond, called the thick and thin diamond. And he chose a special angle for that. The angle that he chose was that such that the area of this divided by the area of this is golden ratio. And there are several golden ratio coming here, not just the area. The angle, this angle is, small angle is 36, this angle is 72. Cos 36 and cos 72 divided by that is again a golden ratio. So the golden ratio coming here. You heard of golden ratio? Have you? Yeah, it's root 5 plus 1 by 2, right? Yeah. Okay. So Penrose's tiling was there, and the quasicrystal diffraction pattern is akin to Penrose's tiling. It's beautiful, isn't it? So you have quasicrystals, which means when you look for Penrose's tiling, what are called aperiodic tiling, the pattern does not really repeat in these kind of things. You might really have many objects you can create. So I thought, the tiling, I brought it back to sort of a quasicrystal structure and so on in chemistry, physics and so on. So they're all united. Sort of we study them as different, but somehow we study some aspects. Yes, yeah. Go ahead. So this is Penrose's tiling. This is outside, I think, his Cambridge office. Outside the lift. In his honor, they have tiled with the Penrose's tiling, the picture that I showed before. Okay?
I spoke to him.
Spoke to him, okay. So he is standing on his tile, created by him. The next picture. Yes. It's again a Penrose's tiling. You can see previous and next, just previous once again, just for. So you would see this here and so on. Now next. Okay, so this, you see the thick diamond, the thin diamond and tessellation, but there is some black stuff behind that, superimposed. Can you recognize something from there, the black stuff? I'll just give you a few seconds or whatever. Kepler's effort. Excellent. Who said this? You said this? Who? Excellent. Very good. Excellent. So you are following. Very good. Yeah. So Kepler's thing. So Penrose was actually inspired by Kepler's tiling to create this. Kepler's effort. He does mention that. So he superimposed, which means there was a pattern there. He superimposed this pattern and got this. Yeah. And there was a pentagon there, and somehow, as I said, something is not possible doesn't really mean it's the end of the world. It inspired somebody, another generation. It inspired maybe a couple of generations later. Penrose to come up with this nice tiling. And Penrose eventually was not really the first one to talk about aperiodic tilings. It's somebody called Ivo Meyer from Israel. In fact, he was given the Gauss Prize in India during 2010 International Congress of Mathematicians. So it's now studied very widely. Next slide, please. So again, since I'm in the golden ratio thing, nature and math, usually everyone talks about golden ratio. I never talked about it. I talked about non-Euclidean geometry. So again, this is the golden ratio. The beauty is about you have this regular pentagon and so on. Then you join these sides, you will get another smaller regular pentagon. And then there is a, for instance, this side, this is regular, this one, and then this one like that. They all increase, the lengths increase in Fibonacci sequence. Fibonacci, or we call it Virahanka Hemachandra sequence, because they also had looked at it. And then there is this kind of thing I just mentioned, Fibonacci kind of thing. So there is this regular pentagon, and you use this side, and then you can all these regular pentagons you can take like that. Yeah, you can do several things. Okay. So this is regular pentagons in golden ratio. Yeah. Next picture. Nature. Can you recognize this flower? I'm sure you can. Yakadhu, yeah. Arka.
And my guess is that you have taken yourself.
I took this picture, yes, yeah. There are two kinds of yakka flowers, one with a nice green and white. And this one, see, isn't it similar to what I showed before? Just go to the previous slide if you don't mind. Especially this one you see. When you take the golden ratio thing, you see it's becoming intensifying here. This next one. I mean, that's what may be happening here. You see, for me, it's just fascinating, yeah. This is worth more than 100 theorems, honestly, this similarity and understanding this. So, the geometric thing that we kind of see, reason out and so on, nature, which means the message I would like to kind of convey in some sense is, nature has found time-tested solutions to many of these things. We have abstracted and did a lot of things, but the far you remove from nature, you're really lost. I don't think human beings should realize that he and she are also a part of nature. Unless we realize that, unless we kind of live close to nature, we are doomed, honestly. I really want to say this strong message, because what is happening around, using science, several things and so on. Science is a great thing. I mean, I'm not ridiculing science, but everything has to be put to good use. If you understand, for instance, an understanding of this flower with the golden ratio for me is good. That's good enough, yeah. Okay? Please, yeah. So I thought I wanted to convey the message by a certain cartoon. It's not a cartoon really. There's an old Chinese saying, I'll read it because it may be small. There once lived a man who learned how to slay dragons and gave all he possessed to mastering the art of slaying dragons. After 3 years, he was fully prepared. But alas, he found no opportunity to practice his skills because there were no dragons left, yeah? So that's a dragon. And then René Thom, one of our fields medalists, he added, as a result, he began to teach how to slay dragons. So I'm sure if we kind of destroy nature, I'm sure we will only have to teach them without showing examples, and that's really a bad world. We shouldn't move towards that. Thank you.
Any questions? Irregular polygon. We have tiled the tiles in such a way that all pentagons, irregular pentagons are the same shape.
Yes.
Is it possible to tile a flow with irregular polygons with different degrees?
Different?
Varies.
Oh yeah, that's what. In the irregular pentagon, the degrees also varied, no? For instance, the 15th one that I showed, all the angles were different. I didn't get your question. Yes, yeah. I thought.
Is the combination of only 5 or 6 irregular pentagons?
Yeah.
Is it possible?
Not 5 or 6. I mean, I call it monotiles. In sense, I need only one kind of irregular pentagon, I make hundreds of them, 100 copies of the same thing.
Same copies.
Yeah.
It's same copies.
Yeah.
Is it possible to make with different copies?
Oh yeah, sure, you can, you can. Yeah. I mean,
The definition
that's
of
what.
tiling is
Yeah. Then what does it mean to say tiling? I mean, tiling means sort of you would want to have one or a pattern proto which you could be able to repeat. I mean, if you have arbitrary shapes, you can definitely do tile tessellation. Basically, you can cut. That's what the masons do. Yeah, you can do that.
Yeah, every
But
gap
yeah. As he says, we just want one formula, or one kind of proto, one type, which we can use. Yeah, that's what. Yeah, with irregular this thing exactly you can do. Yeah, you have a lot more possibilities. Yes, yeah.
Yeah, it's no more of a popular talk, so
Yeah.
you may not have a specific question.
Sure, you may not have a specific question, but if it is inspired, and I have given you many questions to find answers yourselves, many of the simple ones, why is it only 3 types of hexagons and so on? I mean, you might find a proof from the book, but try to think about it and see if you can come up with some proofs. It's nice, yeah.
Yeah. He also mentioned an open problem.
Yeah.
Nobody knows.
Yeah. Beyond 15. So if you find the 16th one, it will be really a startling news, yes. Or if you can show that because the irrational number was there, we know that so many of them, if you can show there are infinitely many irregular ones which can tile, that's again great news, yeah.
It was fantastic conversation. I guess it was really inspiring and we can inch forward to understanding something.
Thank you for your patience, yeah.